All right, so angles and their measure. So they just talk about some terms that are pretty straightforward angle terms. Initial side, well, that's the side where you begin, initial. Terminal side, that's where it ends. The vertex, that is the point in between the two rays, right? And so we're used to angles. We've seen them all the way back from algebra and geometry world. What we've done so far with angles, and we did it in Algebra 2, we did introduce radians and things like that, but really angles are typically thought of as degree measure, okay? And so what they start doing is they start taking those angles and they start putting them on a coordinate plane. And the vertex is at the origin, 0, 0. The initial side is always the x-axis in between the first and fourth quadrant. And then the terminal side is the other ray. And so then you have this angle measure in between the initial side and the terminal side. This is what we're used to. They've just now placed it on a coordinate plane. This right here is called standard position. Standard position. So if you study like in physics and you study vectors, this is also considered standard position for a vector. So if they give you a degree for a vector in standard position, you assume that they're starting at a certain point and going, in a counterclockwise motion, all right? And so that's what it is when it's on the coordinate plane. You're starting here, you're going in a counterclockwise motion, and you are measuring the angle movement from the initial side to the terminal side, okay? So then positive angles are done in counterclockwise. Negative angles would be clockwise, all right? So if I were measuring this angle, I would start here and I would say, how many degrees does it take to get to here? Positive. But if I were wanting to go to this clockwise, then I'm going to have a negative degrees. So I'm actually going to go in a negative movement to go this way, all right? So then we have an entire circle, which we have known for a long time that that's 360 degrees, all right? So then if you take a circle and you divide it by 360, you're going to get 1 degree. And that is the amount of movement that each degree makes. Now you understand too that we can have decimals in there, and so we can have partial degrees as well. But starting at the initial side, you go around, and they have put some pretty common angles here, which you're going to see show up on your unit circle. 30 degrees, 45, 60, 90. And you can see it can keep going past 180. All the way to 360 here. And honestly, because it's a cycle, what you'll see is you can keep going past 360 and you're just starting into your second circle is what's happening when you go past the 360 movement, okay? The first thing we do is then do those partial degrees. Degree measures can also be expressed using degree, minute, second. You will see this in navigation, okay? Because think about navigation, all right? If I am going across the Atlantic Ocean, a degree may not be a small enough measure to make sure I end up at the right spot. Because if I am just 1 degree off and you keep going, so let's say we're supposed to go this direction and we're 1 degree off, the farther I go that 1 degree, when I hit a landmass, I'm going to be thousands of miles off potentially just because of 1 degree. And so just like if I were measuring wood, I probably don't want to just measure it in feet unless I need a whole bunch of wood. If I'm measuring trim, I'm probably not going to say, oh, let's just round it to the nearest foot. All right, we have a problem, right? We're probably going to go inches and probably even partial inches there, right? So when we're measuring, the more precise we get, the smaller the measurement becomes. And so degree is not the smallest measurement. You have minutes and you have seconds, all right? And so you use your knowledge of minutes and seconds from time to actually convert these. So look at these examples here. We have 56.735 degrees. They want to convert this to minutes and seconds. And so what you do is you start with the 56, and you're going to leave that alone. And that's going to be 56 plus your 0.735. right? That's going to be 56.735. So we're going to take that 0.735 and we're going to convert it to the minutes. Minutes. Well, how many minutes are in an hour? 60. So we're going to take that 0.735 and we're going to multiply by 60. All right? And so when you do that, this piece of it becomes 44.1. And that is your minutes, all right? So then we have 56 plus, that's degrees, plus 44.1 minutes. Well, we still have a decimal, all right? So now we're going to convert that 44.1 minutes to minutes and seconds, okay? And so we're going to say, well, that is 44 plus that 0.1. Well, how many seconds are in a minute? 60 as well. So we're going to multiply that by 60 as well. And when we multiply that by 60, you're going to get 6. So that becomes my seconds. And so to convert this to degrees, minutes, seconds, it would be 56 degrees, 44 minutes, 6 seconds. And you can see your little dashes at the top represent that. And that would be converting from degrees to degrees, minutes, and seconds. All right, degrees, minutes, and seconds. So then, to go the other direction, what do you think we do? Instead of multiply, we would divide. Now, keep in mind the division here. So the 32 is going to be the whole part of my decimal, right? So I'm going to have 32 point, and I'm going to take this 5 minutes. What did I multiply the first decimal conversion by? I multiplied by what? 60. So I'm going to take that 5 and I'm going to divide by 60. All right, divide by 60, right? And that's going to give me 0.083, by the way. So 32 plus the 0.083. Then I have the 28 seconds, right? 28. What did I multiply when I got all the way to my seconds? What did I multiply by? But I had already multiplied by 60 once, had I not? So I multiplied by 60 and by 60 by the time I got to my seconds, had I not? So instead of just dividing by 60, I need to divide by 60 times 60. So what is 60 times 60? 60 times 60 is 3,600. So for the seconds piece of it, I have to divide by 3,600 because I have already multiplied by 60 twice at that point. And that's going to give me 0.008, by the way. 0.008. So I need to add those up. 32 plus 0.083 plus 0.008. So when I convert this to decimals, it's going to be 32.091 degrees. Because I have to, line up my decimals. 0.083 plus 0.008 is going to be 0.091. Make sense? So check your work. You should have gotten 213 degrees, 52 minutes, 30 seconds for the first one. And then 89.935 for the second one. All right, so measuring degrees is really measuring your angular movement, What I mean by that is your rotational movement, okay? That is degrees. If you're talking about how much have you moved linear on the circle, then it needs to be in radians. So, for example, if I were going to need to know the length of the string to go around a circle, I would need it in inches. I can't have it in degrees. You can't walk into Lowe's and say, I need 7 degrees of lumber. They'd be like, what's wrong with you?
Get out.
Okay, yeah. So when we're talking about linear measure, meaning I could stretch it out and actually measure it, you're going to see it in radians. When you're talking about angular movement, actually rotational movement, then you're going to see it in degrees.
7 to 7.
And so there are really different reasons why you would use it. But if you look up at the top here, right above this radian measure box here, solving real world problems like surveying and navigation, you're going to see it in degrees. So navigation is obviously one that you're going to see it in. They're not going to tell you a radian measure in navigation. They're going to tell you degrees, minutes, and seconds, okay? Because you're talking about how much, if I am in a boat, how many degrees, like how much rotation do I need to move this boat to be in the right position to keep going forward, okay? However, and that's true for surveying. When I'm surveying a property, I'm going to say degree to degree, right? And we're going to have some degree measurement there. If you keep reading though, you'll see that it says a degree has no relationship to any linear measure, okay? Inch degrees has no meaning, all right? You can't say inches compared to degrees, all right? So then measuring in radians solves this problem. So when you think of radians, this is just a measurement of the linear movement on that circle, okay? Linear movement on that circle. And they convert. You can convert from degrees to radians, all right? And so the first thing that you see is that while a circle is 360 degrees, it is 2 pi radians, okay? So when you see a measurement in pi, you should be in radians, all right? So on your calculator, you see those 2 modes, degrees and radians, all right? Degrees is going to give you degree measurement. Radians is going to give you radian measurement, and they are 2 different things. Think about 2 pi. What is pi? Pi is approximately 3.14, okay? So 2 pi is approximately 6.28. So I'm talking inches. Then 360 degrees, if my circle was in inches, would be approximately 6.28 inches around, okay? So 360 is 2 pi radians, all right? So that is where my conversion starts. And you'll see that they say, well, then half a circle, 180 degrees, would be half of 2 pi. Well, that's just 1 pi, all right? So half of a circle then would just be 1 of the pi's, right? Because the whole circle is 2 pi. Then 90 degrees would be a fourth of it. Well, a fourth of 2 is pi over 2, okay? And then just a sixth of it, 1/6 rotation, would be pi over 3. And so you start seeing this conversion. And so you can convert from degrees to radians and from radians to degrees. There's a formula for it, and it's a really rather simple formula, okay? So if you look at the top of the next page, you'll see the formula. If you have degrees and you are going to radians, you are going to multiply by pi over 180. Pi over 180. Pi being your radian measurement, 180 being your degrees. Remember, you always, when you're converting, you want to cancel whichever one out so that you can convert to the other. So degrees to radians, pi over 180. Radians to degrees, 180 over pi. Okay? So whatever you want should be on top. If I want radians, I should have my pi on top and my 180 on the bottom. If I want degrees, I should have my 180 on top and my pi on the bottom. Okay? Now I will say you're going to have to do fraction reduction here because you don't typically have degrees like a fraction with a decimal as well. Does that make sense? So when you see radians, you're going to see it in fraction form, not typically in decimal form. In decimal form, the pi will be gone and you will have multiplied by pi and changed it completely to decimals. Let's look at these examples. Write each degree as radians and then each radians as degrees. Okay? So the first one is 120 degrees. We want to convert it then to radians. So I'm going to take my 120. Degrees is on top. So that means I'm going to multiply by the pi over the 180 here. Okay? Pi over 180. Which means I can do some cross canceling. Remember that 120 is basically over 1. And then I can cancel. My zeros automatically cancel. What goes into 12 and into 18? 6. So 12 divided by 6 is 2. 18 divided by 6 is 3. This is going to convert to 2 pi over 3. Negative 45 degrees. If it is negative, you keep it negative. So we're going to keep that as a negative. So we're going to say negative 45 times pi over 180, What goes into 45 and into 180? If you don't know a large, start with a small. This ends in 5 and 0. What goes into something that ends in 5 and 0? 5 is the answer. So 45 divided by 5 is 9. And then 18 divided by 5 is 3 with a remainder of 3, right? And then 5 into 30 is 6. 9 and 36. What goes into 9 and into 36? 9. So 9 divided by 9 is 1. 36 divided by 9 is 4. So on top I have 1, a negative, don't forget that negative, and pi. So I just have negative pi, negative 1 pi. And on bottom I have just a 4. Negative pi over 4 is my negative 45 degrees. If you want to write it, you can say, okay, that's going to be negative 45 pi over 180. Now I'm just reducing my fraction. Negative 45 pi over 180, then reduce your fraction and leave your pi alone. Everybody see that?
That's just another way.
Right. Mm-hmm. The other two are in radians. I'm going to change them to degrees. So I'm going to take my 5 pi over 6, and I'm going to multiply that by the 180 over pi. All right? Now here, my pi's should cancel, right? So my pi's cancel here. My 5 cannot cancel with anything, but the 6 and the 180 can cancel, right? 6 divided by 6 is 1. 180 divided by 6, 6 goes into 18 3 times, so that's going to be 30. So now I have just 1 on the bottom, so nothing on the bottom really, right? And then 5 times 30, which is 150 degrees.
So,
all right, the last one is in radians, so we are going to change it to degrees. Negative 3 pi over 2 times 180 over pi. All right, my pi's will cancel here. 2 and 180. 2 divided by 2 is 1. 180 divided by 2 is 90. So then negative 3 times positive 90 is negative 270 degrees. Easy enough. So go ahead and try that. Check understanding there, the guided practice. All right, so check your work. 210 should have been 7 pi over 6. Negative 60 is negative pi over 3. 4 pi over 3 is 240, and negative pi over 6 is negative 30. All right, coterminal. If terminal means where it ends, what do you think coterminal means if you're talking about two different angles? Coterminal means they end at the same point. Okay? Coterminal means they end at the same point. So like the first one, I have this angle here, right here. So I have this angle that they have drawn. I actually have two ways to get there. I have a positive angle, alpha. So if I go counterclockwise, I'm going to get some angle measure here, positive, right? And then if I use beta here and go clockwise, I'm going to have a negative angle. But the truth is they're going to end at the same exact point, right? You can see that. So that can happen. I can go the positive direction or the negative direction and end at the same point. Or another example, I have this angle here, and I have this alpha movement. I start here and I end here. There we go. Or because this is a cycle and you can just keep going, I could also start here, go past it, do a full 360, and then go again and end there. Those are going to be two different angle measurements, right? I'm going to say that's probably 60 and 420 if I were guessing what those angle measurements are. So I could have a 60-degree angle, a 420-degree angle, and the truth is they end at the same point. And what you'll find as you start introducing unit circle stuff, you have this repeated pattern of numbers because it is a cyclic function, is a function that cycles. And so because it cycles, it ends up on top of itself every 360 degrees and every 2 pi radians. You end up back on top of yourself, okay? And so coterminal angles can happen in degrees and radians. And really, in degrees, if you want to find an angle that is coterminal, you could add 360 degrees to that angle, or you could subtract 360 degrees from that angle, and you would have an angle that ends at the same point but has a different degree measure. For radians, you would add 2 pi, or you could subtract 2 pi, and you would end up with an angle that has a different measure but ends at the same point and starts at the same point. All right? And so that's what coterminal angles are. So if I wanted to find it, identify all angles that are coterminal, and I'm not going to make you do all of them. It's just like times 360 in or whatever. But I will make you find a positive and a negative. So if I wanted to find a positive and negative coterminal angle to 45 degrees, I would take 45 degrees and I would add 360. So if 45 degrees is right here, hopefully this is 45 degrees, close enough to 45. Adding 360, right, then I'm going to get 405 degrees. That's a positive angle measure that has the same exact angle measure as 45 degrees. If I wanted a negative angle measure that has the same, I would say 45 degrees minus 360 degrees, because I can go the opposite direction. All right, and I would get negative 315 degrees. And so both of those would be ones that start here and end at the same point. So if I went 360 that way, that's 405. If I went 360 this way, I have moved negative 315 degrees, okay? So coterminal angles, you just add 360 or subtract 360. So then for the other one that is in radians, I'm going to do the same thing, except I'm going to do it in radians. Negative pi over 3 plus 2 pi, and then negative pi over 3 minus 2 pi. Now the difference is I have a fraction, which means I need a common denominator, right? Common denominator. So that's 2 over 1. My denominator for this guy is 3, right? So I'm just going to multiply the top and bottom by 3. 2 is 6 over 3. So negative 2 is negative 6 over 3. And then I just add and subtract. Negative 1 plus 6 is 5 pi over 3. Negative 1 minus 6 is negative 7 pi over 3. That means those would stop and end at the same point. So negative pi over 3, that's going to be down here at negative 60, if I can get it about negative 60 there. All right. This is negative pi over 3. That means 5 pi over 3 and negative 7 pi over 3 would end at the same spot. They would end there. 5 pi over 3 and negative 7 pi over 3 would also end at that same point. That's all you do. You add a full circle, you subtract a full circle. If you're in degrees, that means 360. If you're in radians, that means 2 pi. Add a full circle, subtract a full circle. Arc length. So remember I said that radians give you a linear measure. And so if I'm talking about arc length, then I need it to be in radians, all right? It also depends on how big my circle is, okay? So if I have a circle that is 2 inches big with a 30 degree, and I'm trying to figure out, well, what's the linear movement on that circle, that's going to be a different length than if my circle has a radius of 10 inches. I will have to move farther, right, with a radius of 10 inches than if I have a radius of 2 inches, all right? So think about it, if I were to have a clock and you had a pencil on the second hand, okay? They're really asking how long is the line that you would draw with that pencil, okay? So if my radius of my circle is short, the pencil isn't going to go as far for 30 degrees as it would if it is a long second hand and it goes 30 degrees. It's going to go further, okay? So there's 2 factors that affect the arc length, the length of that piece of the circumference that I'm trying to figure out. The 2 things that affect it is the measure of the angle itself and the measure of the radius. However, because I'm talking about linear measure, a measure of the arc, it must be in radians. So if they give it to you in radians, you're good to go. If they do not give it to you in radians, you have to convert it to radians and then multiply, okay? So the formula is very simple. The formula to find it is the arc length. We denote it as S. This becomes important when we do word problems. S is going to be the radius of the circle times theta. Theta represents the angle measure in radians. Theta is the angle measure in radians, okay? Theta is measured in radians, okay? So find the length of the intercepted arc in each circle with the given central angle measure and the radius. Round to the nearest tenth. Here, pi over 4, they gave it to me in radians. So I literally just multiply pi over 4 times 5. That's all I'm doing. So I take pi over 4 times 5, which is over 1. You get 5 pi over 4. This is centimeters. And I am finished. Very simple, okay? The second one is in degrees, so I need to convert it. So I'm going to take 60 times pi over 180 times my radius. And you can multiply all of those if you want to, and you can do your cross-canceling, right? The zeros cancel out. The 6 goes into 18. Then we multiply across 1 times pi times 2. That is 2 pi. On the bottom, I have 1 times 3 times 1. 2 pi over 3 inches. Now, this said round to the nearest decimal. So if it says that, then we're actually going to take this guy right here and we're going to put it into our calculator because pi is not in decimal form. So if I take 5 and multiply it by pi and divide by 4, I get approximately 3.9 centimeters, okay? Here, if I take 2 times pi and divide it by 3, I get 2.1 inches, all right? And that is all I have to do for arc length, all right? That's all I have to do. Radians times your radius. If it's degrees, convert. 60 pi over 180 times your radius. So go ahead and do guided practice number 4. So check your work when you get it done. Question?
So imagine being the person to discover this and you're like the only one who understands it and like trying to explain it to all these other people who have like barely any education.
Well, so
That would be crazy.
yeah, so degrees and radians are man-made measurements, so to speak. Like if you read the Bible, they'll do things like span, and that's, this, or they do, so they just took a man's average arm length. So when
Until it was like
cubit was like from elbow to tip, span was like palm to tip. And so because, and then they said, well, let's do a uniform measure. So let's create a tool that measures this. And so then that's where we get like meters and inches. And so when they took a circle, they're like, okay, let's divide it by 360. And that's going to be, every one of those is going to be a degree or whatever, so you start running into this Probably because, my guess would be because a circle is a 3-to-1 ratio. If you go back to like biblical times for your pi was rounded to 3 instead of 3.14. So they probably would have chosen something divisible by 3 because they would have already known pi back when degrees would have been started. So my guess is they would have chosen a larger number divisible by 3 because of the ratio of pi in there. But that's just my hunch. I've never really studied when and where degrees and radians came to play.
What were you doing just doing? You know, if I said 3.14 ratio, right?
Well, that would have been the more accurate our measuring devices became. So when God told them to build the altar, they would not have had a measuring device that would have been able to get it in 0.14 measuring devices. So if you look at the circle around the altar, it was a 3-to-1 ratio. It was pi is what it was. But as we get more advanced, to the human naked eye, it would have been for sure.
Yeah.
You would not have been able to tell that. As we got more advanced in our ability to measure units tinier, then we started seeing it. And then as we got computers, then we actually saw that it was a non-repeating, non-terminating decimal, which we wouldn't have been able to do prior to probably computer age. Poor little person calculating pi. All right, homework, and I'm going to take off the last. So you want to review that particular thing because we're going to use that formula in this next thing that we're about to do. So arc length, or the piece of the arc that we're measuring, is going to be the radius of that arc and then the degree or the radians that makes it up. So that is arc length. That is arc length. All right. So then we're going to talk about linear and angular speed. We're actually accustomed to linear speed. Linear speed is what you think of when you think of speed in general. If I said how fast you were going, like, you know, when Bobby runs cross country, I'm talking about his linear speed. So when we have a linear speed, we're saying how far did they go divided by how long it took them to go that far. And that's their average speed, right? Linear. We're talking about the linear speed. And then we introduce what's called angular speed. And that's really how far they went as far as angular in a certain amount of time. All right. So we're going to talk about like rotational speed versus linear speed if you were to stretch it out. And so we have some formulas here that you need to know. All right. Once you know them, you're just going to plug in what you know. But you need to know them to begin with. So the first one is arc length. Arc length is just how long that arc is, and that's just radius times theta, or the measurement of the angle in radians. The next one says linear speed. So this is the next formula we're going to look at, is linear speed. It is represented by the variable v. So your arc length is represented by the variable s. Your linear speed is represented by the variable v, also known as velocity sometimes in physics, okay? Linear speed. This is given by the formula S over T, all right? What was S? S was arc length, okay? So when I look at this formula here, my linear speed is going to be my arc length over my time, all right? So how long it took to go that far, all right? Which means my arc length is radius times pi. So these two are the same thing. Your radius times, not pi, times theta over time is the same thing as S over T, because S is radius times theta, okay? So that's the first one. If theta is the angle of rotation, so theta represents how far we're moving around, then you also have an angular speed. So that's the next one we're going to look at, is angular speed. It is actually, this little W is a Greek letter, but it looks like a W. It's not a W. All right, so this guy is theta, so just your angular measure in radians divided by time, okay? So this guy right here, if I want to talk about angular speed, it's just how far I went in radians divided by time. Very simple, okay? How far I went in radians divided by time. Now, When you look at all of this, the formulas themselves are very simple, but you have to consider everything that's going on in the process, okay? So when we do this word problem, understand that the most difficult part of this is the conversions, because we're talking about inches and they want miles per hour, right? And so the biggest part of this process is just muddling through the conversion pretty much, okay? So let's look at example 5. During one delivery, the tires rotated a rate of 140 revolutions per minute. Find the angular speed of the tire in radians per minute, okay? Radians per minute. So, what is a revolution? Well, that means I went around the circle once, okay? I am talking about in radians. If I am going around a circle one time in radians, how far have I gone? What is one circle in radians? What is it? 2 pi. Okay. It told me how many revolutions I am doing per minute. 140. Okay. So I'm going to take one revolution and multiply it by how many revolutions I am doing, right? So I'm doing 140 per minute. Easy enough, okay? So if it wants the angular speed in radians per minute, that's rather simple. That's going to be 280 pi per minute. And this is radians per minute, okay? Now, they actually multiply that out. So you would put that into your calculator. You would say 280 times pi, and you would get approximately 879.6 radians per minute. All right, so let's look at part B here. Part B. On part of the trip to the next delivery, the tire turns at a constant rate of 2.5 revolutions per second. Find the linear speed of the tire in miles per hour. All right, so now we want linear speed. So we have to then consider what's happening here, all right? The first thing we need to think about is the revolutions. And then we're going to have to go and say, well, how many revolutions is it doing? How big is the tire, etc. First of all, we're going to go back to our equation. Linear speed. That equation is S over T. S over T. Well, what was S? Well, S is radius times theta. Okay, radius times theta. All right. In this case, theta is how many times we are revolving times what one revolution is. Okay. So if I'm talking about my theta here, I'm saying, well, they gave me theta in terms of revolutions per second, right? So if I took a tire and I did one revolution, that would be 2 pi, because that's what it means, right? They said 2.5 revolutions per second. So I'm going to take my 2.5 revolutions. What is theta? Theta is 2.5 revolutions. Well, what's a revolution? It's 2 pi. So I'm going to take how many revolutions I have, and I'm going to multiply it by 2 pi. Okay? So what happens there? Well, that's 5 pi, right? 2.5 times 2 pi is 5 pi. So that is my theta, okay? That's my theta. Of this little equation here, that's my theta. Remember, V can also be written R theta over T, correct? Okay? So I take my theta, and I'm going to multiply it by R. Well, I come up here to my tire that it's given me, and I find my R. Well, my diameter is 30, so way back in like geometry days, radius is 15. So my R over theta, or R times theta over T is going to be R, 15, times theta, 5 pi, over T. So this is radians, right, per second, right? That's what it gave it to me in, 1 second. And actually, we've actually taken this away. This is not going to be radians. They actually gave it to us in inches. Inches here, okay? Because actually it's radians times radius, and our whatever it is going to be inches, because we've actually calculated that arc measure. That is the extent of this. I have 15 times 5 pi inches per second. 15 times 5 pi, that's 75 pi inches per second. The biggest problem here is they specifically told me miles per hour. I mean, that's really my biggest problem here, is I need it in miles per hour, not inches per second. So we just do conversions, all right? And so conversions are always the thorn in our side, I think, when it comes to problems like this, right? So inches. I would recommend starting by changing this little inches guy to feet. That means 1 foot is how many inches? 12 inches, all right? And then we want it to miles. So how many feet are in 1 mile? 5,280, yes. So we have 5,280 feet in 1 mile. So that's that conversion. That converts my inches to miles, which is what I wanted, all right? And then I just need to convert my my seconds to hours, which is easy, right? How many seconds are in an hour? 60 seconds in a minute, 60 minutes in an hour. So there are 3,600, right? 3,600, yes, seconds in 1 hour. The book did it twice. They did 60 and 60, but I mean, we can, that one's easy. I wouldn't want to do the 12 inches and the 5,280. That's just too much. Okay. Now, the only thing I would do as far as cross canceling is make sure that I did my conversions right. Okay. So by that, I mean, I'm going to go through and say, okay, starting here, inches cancel with inches, feet cancel with feet, right? And I am left with miles. That's what I wanted. All right, so I wanted miles. And then seconds canceled with seconds, and I'm left with hours. There we go, miles per hour. After that, just multiply across, divide across, okay? By that, I mean in your calculator, it will do order of operations, okay? So either you have to say 75 times 1 times 1 times 3,600, and I'm saying that just because you may have multiple things, and then divided by, or you need parentheses. So you need to say, okay, I want 75 times 3,600, that's my numerators, divided by 12 times 5,280. Okay, you need to use parentheses like that, or you need to say divide, because if not, you're going to divide, multiply, and that's incorrect, okay? When you do that, you should get approximately 13.4 miles per hour. All right, you should get approximately 13, if it'll let me write it, 13.4 miles per hour. Hopefully. 75 times 1 times 3,600. Yes, divided by 12 and 5,280. Just when you hear this process, theta is going to be the number of revolutions times 2 pi. That is your theta. That's what you're plugging in right here for linear. Radius, they should give that to you somewhere in the problem, whether it's by picture or by verbally telling it to you. So radius times theta divided by whatever it says per whatever. Revolutions per minute, revolutions per second, revolutions per hour. Whatever it said per, that is your time, okay, in units, okay? Make sense? All right, let's
All right, area of a sector. This is actually something that we would have done in geometry, but we would have done it with degrees and not radians. Area of a sector is like, I explain it like a piece of a pizza. You're finding out the area of the pizza slice, pretty much, okay? Whereas arc length, it's the crust, right? Okay, that's the difference. So you're basically saying, what piece of the circle do I have in this little section, this wedge, all right? So the formula is going to be 1/2 r squared times theta. Theta is measured in radians. Must be in radians, just like arc length has to be in radians, okay? Just a formula you're going to just want to memorize, all right? So we're going to take it and we are going to just plug it in. The first one is already in radians for us. That's beautiful, right? So we are going to take the formula, plug it in, 1/2. My radius here is 3 centimeters, so we have 3 squared. My theta is 7 pi over 8. All right. Which gives us 63 pi over 16. Remember, you have 1 over 2. This is 9, so 9 over 1, 7 pi over 8. Multiply crossed. To put it into decimal form, you just literally plug that into your calculator, 12.4, and that is centimeters squared. This is an area, so this is a square, right? This is a two-dimensional. Area is always two-dimensional, so your units are squared here. Linear measure is not two-dimensional, right? So it's going to be 1. This is squared. All right, so for this one, point out a couple of things. This is 130 degrees. So I immediately have a little bit of an issue there because I need this in radians. So if you convert this guy, remember to go to degrees to radians, it's pi over 180, right? So that becomes 13 pi over 18. Okay, so I do need it in radians here. This is the approximate area swept by the wiper blade shown if the total length of the windshield wiper is 26 inches. So the total length of this guy right here is 26 inches. If I want to find just the area that is being wiped, this guy right here, I'm going to have to take this whole wedge, right? And I'm going to have to subtract this wedge that's left down here. Does that make sense? So I have to take the entire wedge and subtract this little guy that is not part of the wiper blade that's hitting the window. So the whole thing, it's going to have the same theta, okay? So it's going to be the 1/2 radius of the whole guy is 26, so 26 squared times my 13, if I could write neatly, 13 pi over 18. And then from that, I'm going to subtract the little piece. Well, if the wiper blade is 16, what's left over is going to be 10, right? 26 minus 10. So I'm going to subtract that wedge, which is 1/2, 10 squared. Same exact angular measure there, 13 pi over 18. Okay? So they're just creating two wedges, and they're subtracting the small wedge from the big wedge to get what's left over. Okay? To get what's left over. And that, again, they plugged it in, 653.5. This is also inches squared when you plug all that in. But yours are going to look more like the guided practice when I give you these. Or if I give you a word problem, you probably are going to do a lot of subtraction there to get the word problem. So go ahead and try A and B. Find the area of the sector. They give you the radius and they give you your theta, but remember theta has to be in radians. So if theta is not in radians, convert it.